over. Okay, so today's speaker is Sam Scibelli, who is a graduate student and an SF fellow at Steward Observatory here at University of Arizona. She works with Yancey Shirley, and today she is going to be telling us about some of her work in star formation and astrochemistry. As a reminder, if you would like to ask a question, please use the raise hand feature under the participants tab, and we will call on you. If it's going to be in the middle of the talk, please only ask your question if it's a clarifying question. All right, take it away, Sam.
Okay, let me share my screen. Okay. It always starts on the 4th slide for some reason, and I'm not sure why. Okay, can everyone see my screen okay?
Looks good.
Okay, so yeah, thank you, Camber, for the introduction. Yeah, I'm a graduate student here at Arizona, and today I'll be talking to you about observations that I've done looking for complex organic molecules in prestellar cores in the Taurus star forming region. So before I get started with the science, I kind of just want to take a moment, and I'm sure lots of people are aware and recognize that more than ever, you know, we are seeing that the humanity and science are not separate. And, you know, whether that has to do with the public health crisis going on or all the social justice issues. So I can't go over everything right now, but I just want to give you an example of something specific to this research, right? I'm using a lot of observations from the 12-meter up on Kitt Peak, which is a sacred site of the Tohono O'odham Nation. And us in Arizona, you know, we are on the sacred site, we are on stolen land. So I just want to take a moment and recognize that, and also point out the fact that currently during this global pandemic, right, a lot of native tribal communities are being disproportionately affected. And so, you know, if you can, you know, there are community relief funds you can donate to, organizations you can volunteer. So I just want to kind of put that out before I get started talking about the science. Okay, so I'm going to go over kind of an outline for what I want to talk about in this talk. I want to basically tell you guys why complex organic molecules are interesting to study and why they're interesting to study in specifically prestellar cores. Then I will talk about kind of what the formation scheme looks like inside, how these molecules are actually forming in prestellar cores. Then talk about this first survey that I did with the 12-meter on Kitt Peak, looking at a bunch of different prestellar cores. Then go on to talk about a specific deuterated species, deuterated methanol, which was a search done by an undergrad in our group. And then I'll talk about the latest survey, this line survey. We actually looked for different levels of complexity within this one prestellar core. And then I'll wrap up talking about next steps and important takeaways. So first, let's talk about why complex organic molecules are cool. So here, I just want to point out, this is a table basically of all the different types of interstellar or molecules that have been detected in space. This is from a recent review by Brett McGuire, and in this paper there were 204 individual molecular species that were detected with 16 different elements, all in the interstellar medium, detected by astronomical observations. So this is a lot, and I just, the ones highlighted in yellow are what I'm considering in this talk as complex organic molecules, or COMs. And so for the definition for this talk is basically anything that contains more than 6 atoms and at least 1 carbon atom. And so the little red arrows kind of show you the complex organics that I will be talking about, the ones that we've detected. So just to give you a little heads up for what I'm going to be talking about later on in the talk. But this is just kind of show you, you know, that this is a growing field. And even as of, you know, 2020 in February, this list is actually incomplete. There's actually 218 molecules that have been detected, not 204. So the list keeps growing, and this is really interesting for not just astrochemists, but for astrobiologists, right? So this leads us to big picture type questions, right? Do the organic molecules synthesized in space, do they contribute to the chemical evolution needed for the emergence of life on Earth? So to highlight this even more and to convince you that this is true, a recent paper basically kind of spells out how these molecules can be connected to life and the search for life and sugars that will be the precursors to life. So in this little scenario on the left, basically it's just a chemical scheme for the types of molecules that would be important for the synthesis of RNA. And so one of the molecules in this diagram, which I've highlighted in yellow, is this molecule urea, which in this paper they detect in this giant molecular cloud at the center of our galaxy. And so this is really exciting because, you know, this is one of the most complex organics that have been found and linked to, you know, astrobiological implications. And, you know, not just this giant molecular cloud, but perhaps the most well-studied is the Sagittarius B2N, which is another, you know, giant molecular cloud. But within this giant molecular cloud, there's hot cores. So specifically in this recent paper, urea was also detected towards this Sagittarius B2N12, so this specific region within the hot core. And so this is, you know, very cool and exciting, but again, these are, you know, well-studied objects, giant molecular clouds that are, you know, hot, forming massive stars. But, you know, for my interests, I want to learn more about, right, low mass star formation. So, you know, Sagittarius B2 is nice. We also detect not just urea, but glycoaldehyde, which was detected with the 12 meter back in 2006. They did a big survey, and there's also many other complex organic molecules. In this recent paper, they do a spatial study of all these different types of molecules towards this hot core. And so this is really exciting. But again, we want to look not just at these hot cores, but at things that are similar to our own solar system and low mass stars. So recent observations of this class 0 protostellar binary, this IRAS 16293, kind of the like typical, like the very well studied core. It's been studied in this ALMA PILS survey, and lots of complex organic molecules have been detected towards this source. And specifically, I show here the connection to glycoaldehyde. So this is really exciting that, you know, this object, which is thought to be, you know, what a similar system to where our sun and solar system form in, is actually detecting these really complex organics. So this leads us into low mass protostars, and these are really interesting sites of star formation, right? And we're detecting complex organics in an increasing number of them, right? So here you see IRAS 4A, which is a very well-studied core, and also there's a hot carino in L1157, which is shown on the right here as well. But while it's very exciting, understanding the initial chemical conditions within protostars specifically is complicated, right? Because there's internal radiation, there's, you know, source confusion, there's multiple sources in them, there's shocks, there's outflows, which shown in 4A, there's which shows outflow directions, and then also there's high optical depths of the complex organics within these objects. So it makes for, you know, if we're trying to understand how these complex organics form and, you know, what the origin of them are, we might want to look at an earlier stage. And this was also true further I guess, confirmed with recent observations as well. So this is just a schematic showing basically, you know, all of the different types of things that go into these low mass protostars, right? You have outflows and you have infall and accretion, shocks, and so there's a lot going on in the hot inner part, right? But recent observations in colder parts of these protostars. So here, example, are ALMA band 3 observations of dimethyl ether in 3 different protostellar sources, showing that, you know, complex organic molecules are abundant and similar in abundances and enhanced in the cold component of low mass protostars. So this even further indicates that, you know, complex organics could actually be inherited from earlier stages, and all this to say basically as motivation that prestellar cores, the phase before protostars, are an important and exciting place to study complex organic molecules. So that's basically what I wanted to convey, is that prestellar cores are what we want to focus on, right? Because they're one of the earliest phases in which complex organics are observed, and because they don't have, you know, internal radiation or shocks, they're giving us a better constraint on initial chemical conditions. So that's what the focus of my work is on, is studying these prestellar cores. And so again, the prestellar cores that I'm talking about in this talk will be forming low mass type objects, and they're very dense and cold, like less than 10 Kelvin objects. And so prestellar cores in and of themselves are interesting objects to study complex organic molecules because they are so dense and cold. It's not quite understood how these molecules are forming. And so what we want to do is try to figure out, you know, when, where, and how are these molecules forming in prestellar cores. But, you know, in order to do this, it would be nice to have a more representative sample of cores. And, you know, only prior to the survey that I'm going to be talking about, only a few well-known dense evolved prestellar cores have had complex organic molecules detected towards them. For example, this L1544 source is a very well-studied, very evolved core. And there's been a couple other prestellar core environments that have detections towards them, as you'll see here. But again, the information about the prevalence and distribution of COMs in a more representative sample of cores is lacking. And so this prevents kind of the testing scenario, or testing of complex organic formation scenarios, which I'll now talk about. So, you know, complex organics are cool and interesting, and they're really exciting to study in prestellar cores, but, you know, how actually are they forming in prestellar cores, and what do we know about that currently? So the basic idea that most people originally thought was, you know, these organic molecules are forming on the ices in the grains, and then those will be slowly irradiated out and by UV and cosmic rays, right? But a lot of the early work found that these gas phase chemical ion reactions were very slow, and therefore they don't account for the abundances of complex organics that we actually see in prestellar cores. However, I do want to note that there are recent works with cosmic ray chemistry that might actually explain better how complex are formed in prestellar cores. But for this talk, I'm going to be talking about ways in which we enhance complex organics in cold and UV shielded environments to match observations. And so the types of reactions I'm going to be talking about are surface reactions and chemical reactive desorption. So basically, in this chemical desorption modeling scenario, you have precursor molecules, so radicals like HCO and H2CO. they are forming on the grains, and then those get chemically desorbed out, and they react in neutral-neutral reactions to form the larger complex organic molecules. So that is the formation scenario that I'm going to be talking about later on, and what we actually think enhances the complex organic molecules in these environments. And there's also different types of surface reactions in non-diffusive chemistry, but I won't get into that into too much detail now. And of course, these models predict abundances, which then we can constrain with our observations. Okay, so enough background. I want to get into the actual results from our survey. So, you know, with all of this in mind, what we wanted to do was basically target a bunch of prestellar cores in the Taurus Molecular Cloud, and we wanted to search for complex organic molecules to see whether or not, you know, they're prevalent in a representative sample. And so we targeted these 31 prestellar cores, which were picked out from previous ammonia mapping results from Youngman Sao et al. And we decided to search for methanol, which, because it's one of the most simplest and should be easiest to detect. And then we looked for acetaldehyde, which is kind of the next level of complexity. And so right away, we detected methanol in 100% of the cores targeted, shown here. Here is basically a zoom in showing the different transitions. So these are 96 gigahertz transition detections. So, and they all are at different upper energies, which is important because this gives us a better constraint on column density and excitation temperature, which I'll show in a few slides. So then we searched for acetaldehyde, and we detected it in 70% of the cores that we targeted. Here is a zoom in again. This is also a 96 gigahertz transition, so these are all 3 millimeter band transitions. And you can see here, while we detected 2 transitions, they are both at similar upper energy levels, so we needed another transition if we want to get, you know, abundances to compare. And so we searched for another transition. This is an 84 gigahertz transition. So out of the 21 cores which we detected the 96 gigahertz transition in, we detected this 84 gigahertz transition in 6 of the cores, which is shown here. So great, we have our detections and observations. Now we want to constrain column densities and abundances. And there are multiple ways, right, that you can do this. One of the most used way is to do this rotation diagram analysis, which, you know, you have, it's an LTE approximation, so you have to assume the same excitation temperature. So, you know, the next best case scenario is to use a program like Radix, which is non-LTE, but again, it assumes that your source has the same density and temperature throughout. So, I mean, what you would really want to do is do full radiative transfer models, but this is obviously more sophisticated and it's not something that we do in this paper, but it's something that will be focused on in later research, or current research actually, and I'll talk about more at the end of the talk. So, right, so for acetaldehyde, we kind of have to do this, you know, LTE approach, this rotation diagram-like approach, where, you know, because there are no collisional rates published for acetaldehyde, we can't use the Radix method. So this method, basically you plot for each transition detected how column density and excitation temperature, what that curve is like, right? So here you can see for 2 different transitions where the lines cross, and that gives you a constraint on excitation temperature and column density. And so we did this for the 6 cores that we have both transitions for, and then we use that median excitation temperature to then extract the column density for the rest of the cores that we observe acetaldehyde in. And so for those interested, here is the range in column density and excitation temperature that we find for those 21 cores. Okay, so Next is methanol. And methanol, we can actually be a little bit more sophisticated and do a bunch of Radex grids. So what I'm showing here is basically on the y-axis is the intensity from our observations minus the intensity from the Radex models divided by the RMS, and this gives you, where this is minimized at the best column density gives you your, best fit. And so we did this for all of the 31 cores and found the range in column density and excitation temperature. Okay, so now we have column density. We can compare to H2 and actually get abundances. So the first thing that we can do is compare our abundances, basically compare core abundances to core abundances by just seeing, how the abundances change with the distribution of cores along the filament. And so what I've done here is basically broken up each region of the molecular cloud where the cores reside in and labeled them more evolved versus less evolved based on whether or not there are protostars embedded in that region. So for example, the red region is considered more evolved because it has a lot of protostellar activity versus the yellow region, which does not. And so what we can take away from just this simple bar graph shows that in the less evolved regions, there is a higher methanol abundance versus in the more evolved regions, there is lower methanol abundance. And so we can kind of investigate this a bit further by doing a very simple virial analysis. This is sometimes known as the alpha parameter, but basically we just take the kinetic and gravitational terms of our cores, and we plot that on the x-axis, and the large plot shows how that methanol abundance compared to H2 falls on a virial plot. And basically you see, right, that the lower in methanol abundance, the more gravitationally bound your cores are. And in the insert panel, that's the same. This is the acetaldehyde to H2 compared to the virial parameter. And so in the paper, we talk about, could methanol and acetaldehyde be chemically linked? I won't get into the details here, but please check out the paper for that. And so, in line with understanding this chemical or this, these evolutionary parameters, we can also compare to these reactive desorption models, which I talked about earlier. So here are models for specifically, these were done for that, well-studied, well-evolved core L1544, but we can still compare, our range of abundances to these models. Finding, ages around 10 to the 5, and also just to illustrate further, right, in the right panels, you see that, without reactive desorption, we're not getting abundances up to the levels that, that we actually are seeing in prestellar cores, even for this representative sample, of course. So next, I just want to point out as well, shifting gears to just looking specifically at methanol, we do detect methanol in every core, so we were interested in kind of understanding, is this methanol, how prevalent is it, and is it just in the prestellar cores? And we can already see from a Linewidth analysis, this just shows the methanol to ammonia. And you can see that, methanol Linewidths are a lot broader than, say, the ammonia Linewidths, perhaps showing that, we're actually sampling larger scale motions within the cloud. And so this kind of gave us motivation to say, well, why don't we try to map methanol in these regions? And so we did. We decided to actually go through and map. There used to be a video at the bottom of the screen, but this is a PDF now, so I just screenshotted a portion of it. But basically, we decided, let's try to map and see, if there's distribution of methanol not just in the cores, but along the filaments. And we do, in fact, see lots of methanol. And again, I just want to point out that this is, with the 12 meter, this is very coarse resolution. So this is like 80 arcsecond resolution. And so we're not actually tracing it at core level, but this is definitely tracing along the filaments. And already you can see that we're tracing different velocity structures. So in the insert panel on the right, you see this B211 region, and at different velocity components, you see one is tracing more the core and the other is tracing along the filament. And this is actually similar velocity components already seen by Hakar et al. In 2013 for the C18O, which you can see here as well. So we decided that we can actually create abundance maps of these regions as well to show further, that methanol is not peaking on the core, but rather that there's more methanol in the filamentary structure surrounding it. So that's what these plots show here. In the bottom panels on the left, it's just the abundance of methanol, and it shows you where the prestellar core 20 is, compared to on the right showing, the core is peaked in the AV map. Okay, so we see a lot of methanol, and there's a prevalence of prestellar cores. Now I will switch gears and talk about a recent survey done to see, well, okay, so we see a lot of methanol. What about the deuterated version of this? So this project was done by an undergrad student who just submitted the paper, so stay tuned for more on that. But Hannah Ambrose, she decided to search for methanol, deuterated methanol, in this B10 region, which is another less evolved region, which showed high abundances of regular methanol. And so they found a 75% detection rate, and in this plot shows you basically the deuteration fraction versus excitation temperature, and they find that on average the deuteration fraction is about 10%. And so this is a really cool survey, because not a lot of, I think this is one of the only surveys to actually search for deuterated methanol in prestellar cores specifically. And deuteration chemistry in its own right is very interesting. And one of the main conclusions, or I guess takeaways from this paper as well, is Hannah plotted basically the fractional, deuteration fraction versus methanol line width, and found that there is correlation where basically the higher the deuteration fraction, the lower the methanol line width. And so, could this mean, right, that, if you have less deuteration, perhaps, that high abundance of deuterated methanol is associated with more evolved cores. So interesting results there. Okay, so last big portion of the talk, I want to talk about the line survey that I've done towards this other prestellar core in Taurus, L1521E. And so, we did look for, methanol and acetaldehyde in a large sample, of course, but we also want to search for even more complex organics and understand to what level of complexity can we actually detect in these objects. And so L1521E was targeted because it's a very young core. This is just showing in the bottom plot, basically it's the C18O to N2H plus ratio, which basically kind of shows you how, like, the CO depletion rate, and L1521E stands out as being very low in CO depletion. And so, and it also, unlike other prestellar cores that have been studied to death, it doesn't show any indications of collapse. the early time type molecules actually peak on the core, such as CCS, versus late time molecules like ammonia are very weak. And so this is, considered a very young core. And so it'd be interesting to search, right, to see, in this specifically young core, can we see the level of complexity that we see in, L1544, which is this very evolved core. And so we do find a lot of complexity, right? So just to show you kind of where this core lies in relation to the other cores that I've presented, it's still in the Taurus Molecular Cloud, but kind of off to the side. But we do detect acetaldehyde, we detect dimethyl ether, methyl formate shown here, and vinyl cyanide. And we tried to detect glycoaldehyde, but we were unsuccessful, but we do present upper limits. So one of the cool things about this survey in particular is, we have multiple transitions of these molecules. So for example, vinyl cyanide, we have 7 transitions and 2 upper limits, which we can use to constrain our rotation diagram, which is exciting. And then acetaldehyde, we have 8 transitions as well, which we can then use for rotation diagram analysis. And just a little quick fun fact about vinyl cyanide, and kind of tying back into the idea that, these molecules are cool and interesting for astrobiology people, is, vinyl cyanide has been thought recently to be perhaps this like precursor that will form like structures of cell membranes for molecules that are important on Titan's atmosphere. So just a little interesting tidbit about vinyl cyanide. So one of the main results, or one of the main interesting things that we did with our detections, was we actually wanted to see whether or not, assumptions that are made about just assuming, right, a filling fraction of 1, or assuming that your source size is much larger than your beam, how does that affect what your column density actually is? So on the left panel, we basically show as a purple curve kind of how your column density changes when you pick different source sizes, right? And so, there is a big difference. So we decided to actually estimate the source size for L1521E based on recent high resolution data from this Nagy et al. 2019 paper, and they have nice maps of methanol. So for this, we're kind of assuming that methanol and acetaldehyde trace the same structure. And so if we use this source size, we actually, are finding that if we don't correct for source size, then column density is underestimated by a few factors, right? And so basically this tells us that, in the future, it's not enough to just have these single dish pointed observations, but it'd be really nice to have higher resolution maps to lower systematic source size error, and to tell, whether or not methanol is actually the right molecule to compare, if methanol and acetaldehyde are actually tracing the same spatial scales. Okay, so another important result from this paper, we actually collaborated with Anton Vasiunin, who does a lot of work with the chemical desorption models. And so what I'm showing here is abundance of various complex organic molecules with respect to time. One of the main takeaways is that, indeed we see that the complex organic molecules are peaking at earlier times for L1521E. And the difference in the models, one on the left shows modeling from a more complicated approach from their recent reactive desorption papers. And so the difference basically is the one on the left, they changed the reactive desorption efficiency based on the surface composition, right? But we're actually finding for L1521E that this more simple approach from earlier works, where basically you just assume a single value of 4% efficiency, does better in enhancing the complex organic molecules in this core. However, as you can see, the black line, which is methanol, is way over estimated, so orders of magnitude higher. So there's still problems, right, with these models, and so in the future we need to be able to adjust, and so yeah, so main takeaway basically is that, you know, the gas phase chemistry and reactive desorption alone is not sufficient enough to explain the observed complex organics in cold cores, because, you know, for this young model, we're seeing enhanced complex organic chemistry. And while we can, you know, enhance the efficiency all we want, if the methanol is going to be orders of magnitude higher, there's something else going on. So just want to point out that there's this very recent paper that just came out on Archive, which actually might have a solution for this. So I've overplotted in their abundance versus time plots where L1521E would fall, but their models were specifically, again, trying to compare to that very evolved core L1544. But you know, the main takeaway just from these comparisons is that, you know, in their model, they have these non-diffusive chemical models where they find that excited radicals that were produced in surface or bulk reactions will actually produce complex organics at high abundances, right? So these three-body surface reactions can enhance complex organics in the gas phase as well. So maybe in the future, we can have some type of synergy between you know, reactive desorption and surface reactions to try to find a best fit model, right? Because their models are also not perfect. They find dimethyl ether, which is in the top right, is being underproduced, whereas methyl formate, which is shown in the bottom left, is actually being overproduced. So there's still lots of tweaking that can go into these models, but it's promising. So that's exciting. And then the last thing I want to talk about for this you know, paper in progress, which will be submitted very soon, is that we actually also wanted to see, you know, how our abundances compare to the different stages of low mass star formation. So here is a plot of abundances of complex organics with respect to methanol, and how those compare at different stages. So in the yellow are dense starless cores. In the blue section are class 0 and class 1 protostars, and the last section are for comets, right? And so, I mean, just what you can see from looking at this briefly is that, you know, there is some chemical link between these different stages of low mass star formation. So it's in our best interest to really get more observations of prestellar cores, more observations of protostars, and really try and understand this chemical link and how prestellar cores are inherited and transferred into other stages of low mass star formation. Okay, so now I'll just quickly go into next steps and important takeaways. As I've mentioned, you know, it's crucial that we actually get higher resolution data. So there is an ALMA Cycle 7 ACA project that hopefully will be taken soon. Well, we'll actually look for methanol and acetaldehyde in one of these prestellar cores to really test if these molecules do co-evolve. So this is something exciting for the future. And I also want to point out, you know, I talked a lot about trying to see whether, you know, if cores are more or less evolved and things like that. And in order to really understand, you know, the evolution of prestellar cores and to make, you know, connections with our molecular line data, we really need a good physical models. And so we have, I have observations from the EROM 30 meter I went to Spain last October to get NICA 2 1 millimeter and 2 millimeter dust continuum, so high resolution data. And so it's in the process right now of doing some modeling in this framework, thanks to Annika at MPE, who had done this for Sagittarius B2N. And so stay tuned for more on that. This will be another focus more for my thesis. So if you're interested in modeling and not so much the chemical stuff, you can talk to me about that as well. So yeah, so I just will go over some, you know, the conclusions basically of my talk. Basically, complex organics are really cool, they're interesting, they're precursors to the simple sugars necessary for life. We observe methanol in 100% of the cores targeted and acetaldehyde in 70%. This is, you know, a very cool, interesting survey because, you know, it's one of the largest to target cores in similar environmental conditions. And also complex organic such as acetaldehyde, dimethyl ether, methyl formate, vinyl cyanide have all been detected in L1521E, which is exciting. And our abundances will provide constraints for astrochemical models. And lastly, to better understand the chemistry and evolution of these low mass protostars, we need higher resolution data, which will be the next focus in my thesis. So complex organics are forming early and often. And if you're interested in my paper, there's a link there. So yeah, thank you everybody for listening.
All right, thank you, Sam. If you would like to ask a question, please use the raise hand feature under the participants tab, and then one of the organizers will call on you. All right, while we're waiting for questions, I don't see any yet. I have a question for you. So okay. In your modeling of the L1521 core, was that a single point model that used like a single value for the density and the temperature, et cetera, or did you have varying physical conditions?
Right, so it was using like a Bonnarevert sphere, I believe, for the density. Okay. Yeah, but it was, I believe it's just a single temperature.
Okay, all right. And then looks like we have a question from Vladimir. Go ahead and unmute yourself.
Yes, hello. This is Vladimir. Yeah, very interesting talk. Thank you for nice presentation. So my question is that, you know, what kind of spectral resolution, how high should we go, you know, to resolve the transitions before the CN 14 to CN 15 and the HCN 14, HCN 15? So is that possible to, in the near future, to quantify the isotopic ratios of nitrogen 14 to nitrogen 15 from those molecular lines?
Right. So, yeah, I think that's possible for sure. And there have been studies looking at the isotopic ratio. The problem with prestellar cores in general, right, is that with ALMA, you can't go to super high resolution because basically like it'll resolve out, right? And so that's why ACA data is nice at a resolution of like 16 arc seconds, which we can begin to look at transitions in prestellar cores. But if you go to higher resolution, like what people are doing for protostellar disks and protostars, you're gonna resolve out the emission in these low mass prestellar cores. I think that if that answers your question.
Yeah, this is very important to quantify the enrichment on nitrogen 15 in those areas. I'm not sure whether we know a lot about it. So we know from the observation of comets, but right. I don't. Yeah. So, thank you.
Yeah. Thanks.
Okay, any additional questions?
I have a question. This is Serena. Yeah,
Hi.
so you mentioned about the glycoaldehyde. There was some on the, you had an upper limit.
Yeah.
Do you have implication from that upper limit?
It's much lower than I think it's like maybe 2 orders of magnitude lower than what was observed in the IRAS 16293 source and what was detected in Sagittarius B2N. Yeah.
So that is actually pretty big implication, I guess.
Right.
What does
Yeah.
that mean? Yeah, the expectation was too high.
Right. So and in a lot of these works too, I mean, glycoaldehyde is considered a hot molecule, or forming maybe not in the prestellar core phase, but in the like warm-up scenario for these protostars, right? So this could be like a confirmation that this molecule probably isn't formed in the 10 Kelvin gas in prestellar cores.
Okay, thank you.
Yeah.
All right. Any final questions for Sam? If not, then I suggest that we all unmute ourselves and thank her for a very interesting talk.
Thank you.
Thank you.
Thank you everyone for coming.